like right now, I want to talk about what you're doing with water desalination. Is it NoNa? Is that how you pronounce it?
Yes.
What is that?
NoNa. So it's like no sodium.
Oh, no NA.
Yeah.
You guys are nerds. I love it.
And there's a little positive, like to indicate that it's a positive ion, because those are the ones. Yeah, it's
great, man.
We're okay if people don't realize that until like the 4th, 5th time they encounter the brand. We like that it's kind of subtle. But yeah, cat's out of the bag now.
Yeah. So what's the main goal of this project?
So that's a big question. We have goals at so many different levels. So in the short term, we think that this project can solve water scarcity for individuals and small communities. So that can mean a bunch of different things. It was actually developed for the military to solve water scarcity for like deployed soldiers who have to be off grid, groups of 10. That's who funded the development of this technology initially. We think that, people who live in hurricane zones, maybe in Florida, maybe in Texas, who are thrust into water scarcity when there's a boil notice or the water stops flowing or there's floodwaters, we think we can solve those people's problems. And sailors also, who have lots of salt water and lots of sun, but not a lot of fresh water. So in the short term, we want to make a product that's just like really good for those groups. Because right now they're using portable reverse osmosis, which we can go into it, but it has a lot of flaws. And that's what we think we can do in the relative short term. Beyond that, we think we have some select advantages over reverse osmosis that can treat a greater number of problems at a larger scale. So, we're looking at things like building, water recycling in a commercial building. We're looking at water softening. We're looking at developing world villages and communities, who need a slightly bigger solution than just the portable one we're doing right now. And that's where we're setting our sights right now. We'll see where the development goes. At this point, we don't think that we will be able to displace reverse osmosis for like large scale desalination and give water to the whole Middle East, but we'll see. We just need to keep developing towards the short-term goals and we'll see where it goes.
Yeah. And then you mentioned that the sailors have this reverse osmosis system. What's your system? Why is it different? How is it better?
Yeah. So reverse osmosis, the way I explain it is that it's basically filtration. So with regular osmosis, you've got water flowing through a semi-permeable membrane. We all learned that in science class. But it flows from the fresh side to the salty side. So you'll make the fresh water salty if you just let it happen. So you reverse the process by shoving a ton of pressure on the salty side and you push out clean water through this porous membrane. It's like a filter. To do that, you need high pressure. You need like 800 PSI. And so you need some high pressure pumps and plumbing, and that all takes a lot of power. So to run that, you need, a generator, you need a lot of batteries, or just like a ton of solar. If you've heard that like desalination is expensive and energy intensive, that's kind of why. You have to push water through this membrane at really high pressure. And also they go bad. They clog, just like any filter will, they have to be replaced. So what we're doing fits in the category of an electromembrane process. So in desalination, you've kind of got 3 broad categories. There's reverse osmosis, there's distillation, which is boiling, distilling, and then there's electromembrane. Reverse osmosis and distillation, that's 95% of desalination. There are some niche electromembrane processes that work by basically passing water through a channel and sucking out salt and the bacteria with electricity. It's great. You don't have the filter problem. You can be more efficient in some settings. And there's a bunch of these different technologies. Electrodialysis is a popular one. CDI is another one you hear of. They all have kind of their trade-offs in their niche that they're really good for. One thing that's unaddressed is a technology that's electromembrane, uses electricity to suck salt and bacteria out of the water, that can remove the salts and the bacteria, the total dissolved solids and the total suspended solids, in other words. So our technology can do that, and that's what's novel about it. So you've kind of got you've got an electromembrane process, no filters, that can compete with reverse osmosis. in a different set of ways than any of the other existing processes. It can have some real advantages, like depending on the setting. For urban scale, municipal scale desalination, the most efficient is still reverse osmosis. And we've not, us or any of the other electromembrane processes, we haven't cracked the reverse osmosis efficiency yet. But
is it just at that, sorry to interrupt, is it just you haven't cracked it at that scale, or
at that scale?
Okay.
At that scale, exactly. So at that scale, the metric is watt hours per liter. Reverse osmosis is doing like 4 watt hours per liter at that mega scale. At the small scale, they're struggling to get close to 10, and we're undercutting that at the really small scale.
Where are you at on the small scale?
Yeah, we're around 10.
So you guys are like similar?
We're really similar.
Or what's the benefit then of, like, why would I choose this system over the other system?
Yeah, so if we can get to parity with the efficiency, then you have the opportunity to ditch all the other woes of reverse osmosis. You're not changing membranes. Every time, if you've got like the most portable reverse osmosis device on the market is like 50 to 75 pounds, and it's quite large. It's like bigger than a carry-on suitcase. And every time you replace the one membrane, it's $300. And it's all high pressure plumbing, so it's quite difficult to do that. You've got to have some savvy to be able to service that machine. So if you think about our device, it's going to be 20 pounds, so it's less than half the size, and that matters if you're carrying it long distances. No filters to change, and then the ease of use is so huge. So first of all, there's the ease of use of changing the filters massively better because there's no filter to change. But then just operating it, you've got this device with reverse osmosis. You have to run this thing at 800 psi, right? So you've got a generator. You're adjusting pressure. You're watching a gauge. And you have to keep it in this range, and it's extremely noisy. You're talking like 76 plus decibels. It's freeway level noise. So it's kind of just like this bulky, difficult to use device. And they can't get smaller, and they can't get quieter, and they can't get easier to use. So we're coming in at, half the size, hopefully half the cost, so much easier to use, and get rid of the membrane replacement problem. We think it'll be a lot more accessible for users, who want to have one in their home or take one in their RV or on their boat.
It sounds like the bullet points that'll be on the front of the box, right? It's
Definitely
easier to service. It's half the weight you can carry and transport it. Low maintenance, no filters. And then if there is some sort of, what type of maintenance would it have? Like, what type of maintenance does it have?
So the maintenance is really, so what you have with this electromembrane process is that you're sucking all the salt and bacteria to one side of the channel, and then you're pulling all the clean water out of the other side of the channel. You get some buildup on the one side of the channel of all the stuff, all the particulates and stuff. So what we can do is it can actually self-clean. So it's an electrode, a positive side and negative side. So if we reverse the polarity and reverse the flow, it can clean itself out. We've been using the same membranes for like 5 years, just in our lab tests, and no issues, no signs of fading. So we don't anticipate any maintenance is the short answer.